Hello there, Mr. Sutton bringing you the AB Calculus Quiz 2, Chapter 5, Practice Solutions on Definite Integrals and RAM. For this problem, if h is differentiable and for all values of x, h of x equals h of 2 minus x, that's interesting, which of the following statements must be true? So first one, they're saying integral from 0 to 2 of h is greater than 0. So basically we're making a commitment here that we've got positive area no matter what between 0 and 2. And I mean, this would be true if we could assume that both of these functions were positive, but what if they're both negative? They could still be both negative in this interval and still equal each other. So because they could both be negative, this statement is not necessarily true. Next statement, h prime of 1 equals 0. And you might be wondering, well, how do I even figure that out? Because all I know about h is that it equals h of 2 minus x. But they're talking about h prime, so this is one of those situations where when all else fails, let's try and make the stuff up here resemble the stuff down here. What happens if we take the derivative of both sides of this equation? Well, on the left side, I get h prime of x. On the right side, I get h prime of 2 minus x times a tail of negative 1. There's a definite negative linear function inside there. So then h prime of x and negative h prime of 2 minus x are equivalent. So based off of that, what happens if we plug in 1 for x? We get h prime of 1 equals negative h prime of 1, because 2 minus 1 is 1. And what does that mean? Well, if I add this h prime over to this side, I've really got 2h prime 1 equals 0. Dividing both sides by 2, I get h prime of 1 equals 0. Or another way you can think about it is if this and this are both the same, the only way that could be is if this unknown h prime of 1 equals 0. So any way you look at it, h prime of 1 has to be 0 for this to be true. So that actually ends up being provably true. And now for the next one, h prime of 0 equals h prime of 2 equals 1. Well, we have this little equation up here for the relationship between h prime of x and h prime of 2 minus x. So if we plug 0 in here, we get h prime of 0 equals negative h prime of 2. And if we're saying that h prime of 0 equals 1 and that h prime of 2 is equivalent, well, that would be like saying over here that 1 equals negative 1. Is that true? Definitely not. These h prime of 0 and h prime of 2 can't both equal 1 and still have this equation come out true. The only way this comes out true is if both of those are 0. So therefore, the only true statement here was 2, so that would be choice B. For this question, g is a function such that g of negative 1 is 0 and g of 2 is 5. Which condition guarantees there's an x between negative 1 and 2 where g of x equals 3? So this is talking about intermediate values. So we're essentially asking for conditions for the intermediate value theorem, the IVT. But let's go through these one by one. So choice A, g is defined for all x between negative 1 and 2. Does that guarantee we're going to hit a y value of 3 between the y values 1 and 5? Well, it doesn't necessarily, because even if g is defined, you could still have a defined jump in there, a jump with a solid dot on one of those endpoints, and then you might just skip over the y value 3. So A is not enough. How about B? G is continuous for all x on the closed interval from negative 1 to 2. Well, this is the condition for the intermediate value theorem, and this guarantees that you're going to hit all the y values between y equals 0 and y equals 5. So this is a big yes. The IVT, which guarantees this, requires continuity. Let's just look at the other ones just to be on the safe side. So choice C, g is increasing on negative 1 to 2. Well, that would be helpful, but again, we still run the risk of having a jump in there. You could be increasing and then jump and then still be increasing, and it would count as increasing on the whole interval. And then D, there exists an x between negative 1 and 2 such that g prime of x equals 5. Well, we're talking about slope now, and slope doesn't really have anything to do with intermediate values. So this is kind of irrelevant. Down here, this option E, the integral from negative 1 to 2 equals 3, we're saying the area under here is 3, guarantees that we'll have a function value of 3, well, the area under there is also kind of irrelevant. And in both cases, even if your slope equaled -5 somewhere on that interval, even if your area came out to 3, you could still have a jump in both of those cases. A jump actually still allows you to take the integral as long as there's no infinite discontinuities. So at the end of the day, choice B is the only one that works here. For this problem, f is a function that's continuous on the closed interval 1 to 3. F of 1 is 10, f of 3 is 18. Which statement has to be true? So here they're saying that f of 2 is between 10 and 18, and that's not necessarily true. Although we're guaranteed to hit all the values between 10 and 18 because we have the continuity, we're not guaranteed that we're going to stay between 10 and 18 for this whole interval. We could stray outside of 10 and 18 when we get to the x value too. We just don't know. So choice B then, f is increasing on the interval from 1 to 3, and it has to increase eventually to get from the y value 10 to the y value 18, but for all we know, it might be doing one of these up and down kind of deals until we get to 18. So you could definitely decrease for part of this, so not necessarily for the whole interval are we increasing. Choice 17, or choice C rather, f equals 17 has at least one solution in the interval. Since we have continuity and we're going from 10 to 18, we're guaranteed to hit 17 on the way. So the IVT definitely applies here because 17 is between 10 and 18 and we have the continuity. So far, choice C is looking like the best answer. Let's just see if we can rule out D and E easily here. F prime equals 8 has at least one solution on the interval. So this is talking kind of like about the mean value theorem, being able to say you have f prime equaling a certain thing on the interval. And the mean value theorem, in addition to continuity, also requires differentiability. And they didn't tell us anything about whether this was differentiable. So we can't make any kind of slope statements just based on continuity. And besides, even if we did have differentiability, if you look at the average rate of change here, you've got 18 minus 10 over 3 minus 1. That's 8 over 2, or just 4. The AROC's 4 here, which doesn't even match the f prime that they were talking about. MVT says AROC and IROC match up, but we don't even have that. And now option E, the integral, the area under the curve between 1 and 3 is greater than 20. Well, that would be true if for most of the interval your lowest y value was 10, and then maybe you just shot up at the end. If it's at least 10 the whole way, you're guaranteed that if you go 2 steps to the right with an area of 10 each time, that you're going to get to 20. But we're not guaranteed that. F of x could very well be less than 10 somewhere in between 1 and 3. It could go down to like -2 million, and that would definitely throw this one out. So choice C then is the only one that we can prove. On this problem, we've got a figure showing a graph of f, and we have a g function that's the integral of f from 1 to some unknown that we can plug in. And they're also telling us this shaded area has an area of 2. Based off of that, we want the value of g of 2. Well, g of 2 is just the integral from 1 to 2 of the f function, which is to say the area between the function and the x-axis between 1 and 2. So that would be the shaded area here. Now, before you just jump the gun and say, oh, that's 2, well, they said the shaded area region has an area of 2, but when we say the integral is the area under the curve, we have to keep in mind where the x-axis is. If the x-axis is above the shaded region, and you're integrating from left to right, this actually is going to be negative area. Since that's negative area, the 2 does play a factor, but it's going to be -2, not +2. So that would be choice B then. For this problem, we have two functions, f and g, that have continuous first and second derivatives everywhere. So we don't have to worry about any jumps or cusps or anything else weird like that. And they're saying if f is consistently less than or equal to the g function for all real numbers, so in other words, the f function is always either matching or below the g function everywhere, which of the following has to be true? So option 1, f prime is less than or equal to g prime, does that have to be true? Well, if f is always under the g function, it still could have a higher slope at certain spots as long as that doesn't continue forever. I mean, if f consistently had a higher slope than g prime, it would eventually catch and overtake g prime, and this condition up here would no longer be true. But temporarily, f can have a higher slope as long as it doesn't keep it up. Same thing with the f double prime. Temporarily, f double prime can have higher concavity than g, as long, again, as it doesn't keep that going consistently. So f can temporarily have a higher slope or concavity and still have a lower y value as long as g is high enough up to begin with. So options 1 and 2 actually are not necessarily true. That leaves us with option 3, or none of the above, right? That's also an option. So option 3, they're saying the integral of f between 0 and 1 is less than or equal to the integral of g from 0 to 1. So essentially saying f always has lower than or equal to area than the g function. And if f is consistently lower on y values or most equal to, this is going to have to be a true statement as long as there's no jumps anywhere. Lower y values are going to mean lower areas, because when you're finding the area, you're essentially just taking a bunch of little distance strips with y values and adding them all up. So 3 ends up being a true statement then, because area is tied in with y values, and so we can choose choice C. On this problem, if f is continuous and x is between inclusively a and b and differentiable on the open interval, we want to know which of the following could be false. So it's basically just true, false all the way down. So first one, f prime of c equals all this stuff for some c. Basically, this is the mean value theorem saying that I rock equals a rock for some c value, for some I rock c value on our interval. Is that necessarily true or false? Well, they told us this function was continuous and differentiable. Those are the conditions for the mean value theorem, so this is actually going to be a true statement because we've met the MVT's conditions. MVT guarantees that I rock and A rock equal each other if you're continuous and differentiable. They equal each other somewhere on the interval. Next one, f prime of c equals 0 for some c value in there. Well, are there any functions that are continuous and differentiable that never take on a slope of 0? Sure, there's lots of functions like that. Probably the easiest one is if you take any non-horizontal line. So like y equals x or y equals negative 3x, those are never going to have a slope of 0 because they have a constant slope of something else. So this statement is actually false for this case and plenty of other cases as well. If you take a look at an exponential function, that's also continuous and differentiable and never has a slope of 0. It gets pretty close, but never quite gets there. So B is looking like our answer, but let's see if we can rule out the other ones just to be on the safe side. So C and D, they're kind of the same sort of deal. They're saying we have either a minimum or a maximum value on the closed interval, and that's actually true based on what they told us here. They said that we are continuous on this is a closed interval from A to B. So the extreme value theorem then guarantees that we have a max-min with a closed and continuous function. And then for choice E, they're saying the integral from A to B exists. Well, if our function is continuous on the interval from A to B, then the area is going to have to exist. Area under a continuous curve is always going to be defined. So in this case, then, it does look like choice B is our answer. For this one, if f is a function such that f prime exists for all x, and f is greater than 0 for all x, which of the following is not necessarily true? So let's translate what they just said here. If f prime exists for all x, that means that our function f is differentiable because f prime exists everywhere, and therefore it is also continuous. And this bit here is just telling us our function is also positive. So a good example of this, if you want to just try to picture one of these, is like an exponential function. That's continuous, differentiable, and always positive, assuming it doesn't have like a negative out in front of it. All right, so with that as kind of our mental guideline, which of the following is not necessarily true? So first one, they're saying integral from -1 to 1 of the function is greater than 0. Well, this has to be true. If your function is always positive and it doesn't jump around anywhere, then you're going to always have positive area. Positive function means positive area. So this one we're going to eliminate because it is always true. Next one, integral from -1 to 1 of 2 f of x equals 2 times the integral of f of x. This is going to be true. This is just one of our rules of definite integrals. You're allowed to take a constant that's being multiplied by the integrand and just move it outside. Moving on then, next one, integral from -1 to 1 equals 2 times the integral from 0 to 1. So they're essentially saying that instead of taking the whole area under the curve, you can just kind of chop it off and take half of the x values and double that area, and that'll give you the same thing. Now this will be true if you have a symmetrical function like y equals x squared, which would also meet these conditions here. But what if you don't have a symmetrical function? What if you have like an exponential function? Then taking the area between 0 and 1 and doubling it is not going to give you the same thing as taking the area from -1 to 1, because that -1 to 0 part of an exponential function is less than that other part. So this is false if our function is not even. So C is probably going to be our best answer here, but let's just look at the other ones to be on the safe side. Here they're saying the integral from -1 to 1 and the negative integral from 1 to -1 are the same. And this is true. If you negate the integral, you can switch the limits of integration around and end up with something that's equivalent. So this is a property of definite integrals, so that's true. This next one, integral from -1 to 1 equals -1 to 0 plus 0 to 1. This is also true. This is the additivity principle of integrals, so another property. So then C is the only one that's not necessarily true. For this problem, we're given that the integral from a to b is 5 for the f function, and the integral on the same interval for the g function is -1. What's true based off of that? So option 1, f is greater than g for all x's between a and b. Well, the overall area is definitely bigger. No one's arguing that. But we could certainly have specific x values at which g takes on a higher value than f, as long as those get offset by enough other places. So this is not necessarily true. If f could be less than g in some spots, even though the overall area is greater. Next option, the integral from a to b of f of x plus g of x equals 4. So they're essentially saying, since these have the same limits of integration, we can add the two functions together to get kind of a combined area of 4. And this is true. This is one of the integral properties that you may have seen. Option 3, basically the same idea as option 2, but they're saying we can multiply the areas of the two integrals together to get kind of a combined multiplied area. So for this one, this is not one of the properties of integrals, but we can actually disprove it pretty quickly, if you're not satisfied with not being an integral property as a reason for excluding this. So consider the integral from 0 to 3 of 1 dx and the integral from 0 to 3 of 1 dx. So these are two different integrals, even though they look exactly the same. Now we know that just one of these, if you're taking the area from 0 to 3 under the horizontal line 1, that's just an area of 3. So the question is, if I multiply these integrals together, or if I multiply these internal functions together, is that going to give me an area of 3 times 3? If I do the integral from 0 to 3 of 1 times 1, which is essentially what you're doing up here, f of x times g of x, is just f and g are both exactly the same here, is that going to give me an area of 9? Well, of course not, because this 1 times 1 is really just 1. This integral is actually the same as this integral, so it has the same area. It has 3. Its area is not 9. So this one case here, we just needed one counterexample to knock this one out of the water, and we got it. So option 3 can't always be true, if it's ever true. It might be true in some weird cases, but it's definitely not true here. So the only one that was true then was option 2, which means choice B is our answer. For this problem, we're doing some good old-fashioned integral properties. We've got one integral from 0 to 1 of the f function that equals 2, another from 0 to 4 of the f function that equals -3, and then we want to find this other integral from 1 to 4 of 3f of x plus 2. So we're going to break this up and use some of our properties here. I'm going to start by splitting this up into the integral from 1 to 4 of 3f of x plus the integral from 1 to 4 of 2. And while I'm doing that, I know that if I have the integral from 1 to 4 of 3f of x, I can take that 3 outside as a multiplier by that whole f integral. And then I'm adding to this the area that I get from taking the integral from 1 to 4 of 2 dx. So I just split this up and took out the 3 for one of those things. Okay, moving on. The reason this is not really kind of a final step for me is because I don't know the integral from 1 to 4 of f of x dx. I know the integral from 0 to 1, and the integral from 0 to 4, I don't know 1 to 4. So I'm going to have to find a way to kind of piece these two integrals together to get this integral. So I could express this integral here as 3 parentheses, and now the integral from 1 to 0 of f of x dx plus the integral from 0 to 4 f of x dx. This is just kind of my additivity property going in reverse. I know if I add two integrals together and the upper limit of one and the lower limit of another one match and it's the same exact function, I know that I can just combine those to have the lower limit of the one and the upper limit of the other. Essentially this integral up here. So I can split it up like that as well. Now I still have this plus integral from 1 to 4 of 2 dx out there. I don't want to forget about that. But now we are at the point where we can assign a number to everything because we know more or less what all these integrals are. So I have 3 times, and now the integral from 1 to 0. Well, I have the integral from 0 to 1 of f of x dx. That's 2. If I switch the limits of integration, that negates the area. So it's kind of like basically you're integrating backwards. So that gives me 3 times negative 2 then, plus the integral from 0 to 4, that just straight up is negative 3. They gave us that one. Plus, what's the integral from 1 to 4 of 2? Well, you're essentially taking the horizontal line 2 and getting the area under that over a distance of, let's see, 4 minus 1 is 3. So we have a base of 3, a height of 2. It's just a rectangle. That's going to have an area of 6. So then I have 3 times negative 5 plus 6. 3 times negative 15, or negative 5 is negative 15. Add 6 to negative 15, we've got negative 9. Choice B. On this problem, they're telling us that the f function equals the g function plus 7 on the interval from 3 to 5, which is actually pretty important because they then turn around and say, hey, find the integral from 3 to 5 of f of x plus g of x dx. Well, I'm going to start right off the bat by replacing the f function in here with g of x plus 7. And I'm allowed to do that because they told us that these were the same thing on the interval that's involved in this integral. So this is now the integral from 3 to 5 of g of x plus 7 plus g of x. And, I mean, it's kind of silly to have all of these different things here. I'm just going to combine these. So this is going to be 2g of x plus 7. And at this point, I have to try to turn this into one of the answer choices. Now, the good news is we don't actually need to know what g of x is because it's in all the answer choices, so they don't expect you to do anything with that, really. But we do have to split this up using integral rules. So first thing I'm going to do is I'm going to split this up to be the integral from 3 to 5 of 2gx, g of x dx, plus the integral from 3 to 5 of 7 dx. So just since I'm adding these things together inside an integral, I'm allowed to split it up into two integrals with the same limits of integration. Next, this first integral, well, I can't really do anything there except move a 2 outside, which doesn't seem like much, but it at least lets us match this up with answer choices A, B, and C. So we can definitely say that D and E are not going to work because we have this 2 here. But now we have to figure out what is the integral from 3 to 5 of 7. We need to know which of these constants, 7, 14, or 28, we're going to end up turning this into. So this is essentially a rectangle. You have a base of 2 because you're going from the x value 3 to 5. You have a height of 7. This is just a horizontal line at y equals 7. 2 times 7 gives us 14. So we end up then with all this stuff plus 14. And that's going to be choice B.